Guys, well, welcome. I'm glad you guys could join us. So, my name is Joey, and I work here for Techstar. I do a lot of the training here. I'm also a field service technician. I work in the field, do nuclear startups, things. So, I've also got Emily here with us. She's our customers
Experience coordinator.
Big word there. I guess my new title here that they've given me fancy things.
Yeah.
Lead unit
Hi everyone,
technician.
thanks so much for joining.
Anyways, so we're here to talk about nuclear today, nuclear gauges, and I'm gonna get into that real quick. We're gonna go over just some basics through all of it. At the end of the presentation, we'll let you guys give you a chance to ask any kind of questions or anything you have. So I'll try to allow time for that. Before we get going, here at Techstar, one thing we're really excited about that we have is we have a new training facility. So some of you may have seen it. Our training facility we just built. It's pretty much it's a little mini unit, and this is where we'll be doing all of our in-house training. So anybody here that's interested in training or just wants to come check it out, and we'd love to have you. And like I said, we're really excited about it. The times that we're in today is kind of I guess slow down some of our people being able to come in and see it in person, but that won't last forever. So once this lets up, we'll be able to let people come in here and play with the different devices that we have. But I got a short video I'd like to show real fast on it, and then we'll get into nuclear. Okay, well, that's our little training facility there, and like I said, we're super excited about about it. And if anyone's interested in coming by and checking it out, just let us know. Go through Emily, and we'll be more than happy to just take a tour and talk about it. So let's get going on what we're here for today. So this is going to be we're going to talk about. I'm really going to start off from the basics. It's going to be a little bit of a 40,000 foot view, and then we'll dig a little deeper. So principles of radiation-based measurements, the technology, and then different applications. I'm also going to get a little bit into commissioning a little bit, talking about if any of you that have worked on this before, counts is basically the unit of measurement that we use on our gauges. You've probably also heard milligram and microgram. Those are units of measurement. Typically, when we use milligram and milligram, that's more of our survey or safety side, telling us how much radiation we have. When we talk about counts, we're talking about what the instrument is seeing. So, anyways, let's kind of move on from that. So, or components that you basically have on a nuclear system, on a radiation basis. First of all, you have to have a source. Okay, that's where my radiation is coming from. Typically in nuclear gauging, we're going to use cesium-137. It's going to be our most popular. It has 30 years as its half-life, and that's the reason why it's used so commonly in nuclear gauging is because it does have 30 years of half-life, which means if I started off activity, I'll go ahead and back up on that. Activity is measured in curies or millicuries is usually what we're on most of our nuclear gauging on our vessels. And so when I say half-life, I mean if I started off with 100 millicuries and I have a 30-year half-life, then in 30 years I'll have 50 millicuries. So that doesn't mean it won't still work. It really depends on how strong the source is that you started with. But I'll get more into that in a second. The other thing you have outside of your source, I'm also going to say you also have, some of you may have heard of cobalt-60. It's got a 5-year half-life. They're application dependent on usually which one's chosen. For most applications, cesium-137 is the go-to because of that longer half-life. Cobalt-60 is, to put it simply, has more penetration power. So if we have really thick walled reactors, sometimes our application engineers might choose cobalt-60, but for typically you are going to see cesium-137. So that's our source side. Then on the other side, we have a radiation detector. Okay, for continuous level, as you see in this picture, you can see it's going throughout the entire measurement span. And if it's not for a continuous level, let's say it's a switch or it's a density, then it would just be in one small area. And then you have your vessel itself. So that goes into the equation. And then you have your actual process itself, okay, which is going to be variable. So everything is fixed except for your process itself. Really, radiation, and you're probably going to hear me say this a couple of times in the presentation, geometry and physics. What you're going to hear me say is geometry is everything and radiation does not lie. And if you remember those two things, you can pretty much figure out just about any radiation measurement kind of problem, because it's all about geometry and the radiation is speaking to you. It's physics, it doesn't change, it's very constant, and whatever you see on the other side of that vessel, it is what it is. It's just a matter of interpreting why you're seeing what you're seeing. So to get a little more into it, basically as radiation passes through the vessel walls, it's going to be, we're going to talk about scintillator technology first. It's going to be interpreted into light pulses as it passes through the wall, and the gauge is seeing those light pulses, and those light pulses are going to be turned into counts. Okay, so that's the unit of measurement the gauge is seeing. You're going to hear when you hook up to a gauge and you're doing your calibrations, you'll see counts on your screen. That's the unit of measurement. Everything is going to react with the radiation. Okay, so everything is attenuated. So your vessel wall, the thickness of that vessel wall is going to have a certain attenuation factor to it. The vapor space or the air has a certain attenuation factor to it. How far away the detector is from the source all depends on how much radiation is actually passing through, and then the level of the actual product itself. So here's a kind of just another picture of a way a vessel might be on there. We have collimation angles, which that beam, if you look at how it goes across, your typical angles from that radiation is basically what you have is you have a small pill inside of your source. That's where the radiation is. It's the cesium-137, and that entire big source holder is nothing but lead. Okay, and it only lets the radiation beam pass out in the angle that we want it to pass out. So it has a 45-degree angle cut into it, and radiation is painting a small portion of your vessel and about maybe a foot or two, maybe about a foot's area on the other side of the vessel with radiation. Okay, 45 is very common, beam angle for your radiation. Another one is going to be 60 degrees. So if you have a horizontal vessel, what you will do is you'll install your detector at an angle to the vessel that creates that beam going straight across, which will allow the other side of the beam to go all the way down. Okay, so it's basically you'll have a 60-degree collimation angle on your horizontal vessels, and then on your vertical vessels, it's typically 45 degrees for continuous level. If you're looking for switching, you'll have 0-degree beam angle, which means it's just shooting a small beam across. And you have something on the other side telling you that beam's blocked or not. You also have there's 15 degree. There's different beam angles out there. The most common that you're going to run into for continuous level is 45. The most common you're going to run into for switching or for density is 0. Most applications, in this picture, they're kind of showing you your vapor space you have there. So if you could kind of picture, I'm painting this vessel with radiation, right? I have a 45-degree angle that comes across. My source will be mounted at a level to where I want my 100% to be within that level of where I want my radiation to be. I want my 0% on the bottom. Everything attenuates radiation. Okay, so your vapor space plays a big role in this. When we do our calibrations, whenever you guys are getting, I know Cody, you mentioned earlier that you're getting ready to do a calibration. I'm not sure if this was continuous level or not, but what we're really looking for whenever we do these is we want to be at process conditions, okay? Which means it's usually during startup. So let's say this vessel has 100 pounds of vapor on it. Whatever the vapor is that you're running with, we would like to have that 100 pounds of vapor and the same kind of vapor, because different vapors are going to have different densities. So the closer we can get to those real densities in our vapor space, the better. We also got to think about the different vessel conditions and what can affect radiation, right? So say I have a water jacket that runs around. That's a cooling jacket on my vessel. We want that to be in normal conditions. If it normally runs and it's full of water and it's heated water, we want it to be at that same temperature whenever we get ready to perform our calibrations. If it's oil, I see dialtherm used a lot. We want it at the temperature and to be circulating whenever we start our calibrations. So just talking a little more about physics, about radiation. So like we talked about attenuation. On the process medium itself, most designs are designed in a way, whenever it goes through application engineering, where they want the process to block 100% of that radiation. It doesn't always, and that's where multi-point calibrations come into play. But in most cases, we want it to block. We want to block all the radiation. And in the vapor space, of course, it's going to pass through the vapor space. Some of you heard me talk about the half-life value of radiation. Well, we also have shielding, where we will reduce the amount of radiation. So, to give you some examples of what will reduce a 1/4 inch of lead will reduce your radiation field by 1/2. Okay. Basically, if I had a 100 millicurie source, I put a 1/4 inch of lead in front of it. Now I'm dealing with a 50 millicurie source. And you can see your different half value. That'll block my radiation by half. So different applications that we can have. You can see we have continuous level. Okay, continuous level means that I am measuring from a 0 to 100%, right? Typically, we're using 4 to 20. And a level width, we usually want to know either a high level or possibly a low level. And then we have density. Densities, we want to know what the density of the process is. Really neat things about radiation, the reasons that we use them. It's one of the things that it's expensive, and there's a lot of regulations to it because it can be unsafe. Typically, the way we use it in a plant, we follow all these regulations and we're very careful with radiation safety. All fields that people can travel into have to be under 2 milligrams. So there's a lot of safety considerations, but it works when other things don't. If you have a really dirty process, radiate is something that's maybe a reactor of some kind that has elements in it and process conditions that some other devices don't necessarily work really well with, works. And also it can be applied to the outside of the vessel, so you don't have to have penetration points in the vessel. You can mount it on the outside of the vessel, and it's for the most part a simple installation. So let's talk about installation and a little bit on our spans, our measurement spans. So you used to have two different pictures here, two different vessels. So like I said, most of our collimation angles, our beam angles, will be 45 degrees. When you look at the back of your source holder and you look at the model number, you'll have whatever the model number is, and at least on a Vega, it'll say like dash, and it'll have 45. That tells me I have a 45-degree beam angle, or it'll have a dash 0. So if I have a 45-degree beam angle, then I can pretty much say that if my vessel is 10 foot tall and my source is over here and it's 10 foot wide and my detector is over here, that 45-degree beam angle is going to cover, as far as geometry goes, it's going to cover my entire path. So my 100 ends up being at wherever the center of that source order is. That'll be my 100% point. That's as high as I can measure. Can't measure any above that. So wherever my source holder is mounted on my vessel, and wherever my detector is on the other end of that vessel, be within that range that we want our 100% measurement to be. Okay, 0% would be however far that source is capable of reaching. Now we can use multiple sources. So where one measurement ends, another one begins. So if I need to put 3, 4, 5, I'm sure some of you guys have seen where you have several source orders measuring one span. When your stuff goes through application engineering, we'll usually get some sort of drawing back. And I think I have an example of that in here that'll kind of show you your spacing between your source orders and your elevations of your detector. And you just want to follow those. So your first example, this is usually where I answer a question, I ask a question, wait for an answer, but we're not going to do that right now. But usually I'll say, well, I measure all the way to 0 here. Answer is, I'm probably not going to be able to read a very good 0 there. I might have a little bit of radiation leakage on the other side, or I get a little below it, but my resolutions can be horrible. And if I was out doing a calibration in the first picture there, I would tell you we either need to drop our 100% and lower it and lower our source order a little bit, or we would need to raise our 0. One of those two things would have to happen. Or a third option would be to add another source holder to the measurement so that we can get our full span. If you do require a full span, and shrinking it's not a possibility. In our second picture we have here, you'll see my 100% looks good, right? You can see the dotted line goes across. It's going to reach just fine. But then my 45-degree, where my 0 is above, and I've got radiation coming below it. That's perfectly fine, okay? I don't have an issue with that. That'll work. The only thing that we might want to look on this one, if I was doing this commissioning, is that field below the detector where that radiation beam is still shining. I would use my Geiger counter in that area. For those of you that don't know what a Geiger counter is, I have a slide showing one, and I'll talk a little bit about it, but it's basically the tool that we use. It's a handheld where I can find my radiation fields. I would just do a check in that area and make sure that it's my radiation levels are within safety standards of people being in that area. And outside of that, that 0 and that 100% would work just fine. Well, I'll talk a little bit more about calibration in a minute. We'll see on installation, but I might come back to the slide and talk a little bit about that. So this is a top-down view. Okay, if I were to look, this is a looking at what a beam angle would do, and this is more on the side to side. So I told you have 45 degrees going across. Your strongest beam is going to be directly across from your source. That's typically where you're going to want, wherever that source is pointed, strongest area, your strongest radiation field is going to be right there. That's really where I would like to have my detector at. I still will have some radiation 5 degrees to the left and right of that. And it's just the way that the scatter of radiation works. But my strongest field will be in the center. If I'm a little bit to one side to the other, it's okay. But typically, you would like to get as close to the center as possible. The way that we check that in the field, again, is we use our handheld Geiger counter. We would install our source, have it installed, we'd install our detector, or at least know where we wanted it. And then I would get my Geiger counter and I would move it throughout that area. And I would look at my beam angle, not my beam angles, I'd look at my radiation fields and I would see where my strongest field is. Or I would install my source holder, turn it on without my detector installed, find that strongest area, put an X on it so I know where I want to mount my detector and mount it there. So I talked about this a little bit earlier. I guess I have the same picture up at least. We talk about linear, how linear the vessel is or how linear we want our measurement to be. Our strongest, I'll ask the questions and let you just answer them yourselves, okay? So looking at this picture, where do I think, if radiation is going to pass through that vessel, and there's a couple of things, the things that affect my radiation field. One of the things that affects my radiation field is going to, of course, be the things it's traveling through, right? So any of my process, and it's going to be my process path and the thickness of the steel or anything it's passing through. The other thing that affects it is the process length. Okay, so how far is it traveling? So the further that radiation travels, the weaker the radiation will get. So where is my strongest radiation field going to be in this picture? Answer it in your head, and I'll tell you that it's going to be right up top. Okay, so that's where my strongest field is going to be. And then where is my strongest, and then the weakest, if my strongest is at the top, where my 100% is in this picture, that means my weakest part would be at the 0. So on my detector, what's going to be the most sensitive part of my detector and the least sensitive part of my detector? So the answer to that question is my most sensitive part of the detector will be towards the head of the detector, okay, because the light beams don't have to travel as far. My least sensitive part will be towards the end. So a good installation practice is to invert it. You'll have your the bottom end of your fiber bundle and the head at the 0. You don't have to do that, but that does give you a more linear measurement. When I say linear, I mean that more possibilities of just being able to do an open and closed shutter. The gauge will be able to calculate where, if I just were to take a 0 point on my calibration point and a 100% calibration point, the measurement will be very linear throughout the field. So when the gauge says it should be 10%, I'll be close to 10%. When it says 20, I'll be close to 20. You don't have to do as many calibration points in between. Okay. It moved off of it. So radiation does not lie. It's either there or it is not, right? Geometry is everything. And we must remain constant. So for you guys that end up troubleshooting and you're going out and you're trying to figure out what's going on, there's going to be times when you're going to doubt this radiation thing does not lie, but it is everything. Okay, so and I can even give you some examples. I've gone out and I've gone out to a vessel. I've had operations tell me this vessel is 100% full, but my gauge is reading 0. There's something wrong with my detector. I can tell you, I guarantee you, my vessel's full. Look, I have a sight glass. My sight glass is saying it's 100% full. Heck, I have 2 sight glasses on this thing. They're both reading the same thing. Everything I'm seeing says it's 100%. There's no way that there is any process inside this vessel. And I come up to it and I check it out, and I use my Geiger counter. I know you probably can't see real good in this picture. I have another picture of it, or I'll turn off the PowerPoint and show you. But I use my Geiger counter, and I run it through there, and my Geiger counter is telling me the same thing that the detector's telling me. Okay, and I can look at this and say, well, it's not 100% full. I have my radiation. I mean, it is what it is. I have radiation here, and they go to check in or whatever the case may be, and they find out that their sight glasses are stopped up and it's just holding liquid in there, or they have a valve closed, whatever the case may be. But this will tell you. I've also had situations where I've gone in and I've done. We'll talk about this in a minute, but you'll go in and you'll do what's called a radiation survey of whenever during your commissioning. I like to measure my entire radiation field. I'll start off at the top, and every foot or every 6 inches or whatever I decide on, I'll take a radiation reading and I'll write that on a piece of paper. And I know, and I'll write down what the process conditions are at the time, whether I'm at operating process conditions, completely empty or whatever they are, and I'll put these radiation fields down. Then later on, as I come back 5 years from then and I check it, my radiation field should be fairly close. I may have a little bit of change from the decay of the radiation, but it's going to be very minor. But if suddenly, as I'm checking, I see one area of this measurement that has just hardly any radiation, I'm like, man, I've got an area here of 4 feet or 5 feet that there's absolutely no radiation right here. That tells me something happened inside the vessel. I have buildup in there. I have maybe this particular vessel had trays in it and a tray has fallen. It'll tell you a lot of things. So radiation doesn't lie. It is what it is. Trust it. The trick is interpreting what it's telling you. It's telling you something, you have to understand it. Geometry is everything, which means if geometry is wrong, so is your measurement. If I'm trying to make a measurement here and I have my source pointed this way across, and I installed my detector way up here, and I'm suddenly coming out saying, hey, this thing never goes to 100%. Well, it's not. Or actually, what will happen is it's going to go to 100% early, because it's going to go and it's going to start filling, and it's just going to run out of space. I'm not going to measure this top portion. Well, it's because I've installed my detector too high. It needs to come down, or these things need to match up. So geometry is important, making sure our angles are important, and just remember those 2 things. Just talk a little bit more about orientation. You can see here there's a couple of pictures. One of them shows the inverted detector. One of them shows the detector not inverted, and it's the one on the right, detector's up top. Both of these will work. You know, it's just if I've got a preference, I usually do like inverting the detector, because like I said, I'll get a more linear measurement. A lot of times you'll even see it inside your paperwork whenever you get it in from the manufacturer when they've done their application engineering. They'll tell you whether they've designed this to be inverted or not inverted. Sometimes they put it inside of in there where they'll say, hey, this was an inverted installation, and they'll show the picture just like this. So this is kind of showing you here. This is actually what you'll see, a drawing like this when you get your when you do your application engineering and you get your paperwork back showing you kind of the orientation, you'll see that you've got 45-degree angles. Okay, you can see where each one of these pass and they kind of intersect on the right-hand side, so that I'm fully painting this vessel with radiation in this picture. Also see that I have, it looks like a high level switch on this particular one and a low level switch. So I have both. And this installation looks fine. We'll measure all the way down. You can see where my radiation beam on the bottom passes. I'm going to measure all the way down to that point. As long as everything is installed in the right location and it's where it's supposed to be, I should have absolutely no problem with this. Looks like I have two continuous level detectors. When you do this, there's actually an ability where they can put both of these detectors together to extend the length. So say I'm trying to measure 40 foot and I've only got a 20-foot detector, I can put both detectors together and make it one measurement, or I can do both of them separately. Depends on how I want to bring it into the house, right? I want to measure, say, 0 to 100% on the bottom detector, and then I know that when I'm leaving that bottom detector, it should be at 100, and then my top should start to fill, and you're just going to show 0 to 100. Some places decide to do it that way. That's how they prefer to see it. Other places say, I want that entire measurement. I want it to be 100 and 0 to be 0. So back to installation of the source and the detector. Things to consider: your elevation of the detector in relation to the source. We've talked about that several times. Orientation of the source in relation to the detector. We've talked about that as well. Your total span of your measuring range. How much do I want? What's my span going to be? Installation of your detector itself. How are we going to install it? Where are we going to install it? Right? Are we going to put it on? We need to get it in the center of that radiation field. So as level goes up, counts go down. As level goes down, counts go up. So it might be a little confusing when you first hear it, but think about it. Counts, right? So let me rephrase this. As level goes up, radiation goes down. As level goes down, radiation goes up. So it makes sense if I have if all my detector is doing is reading the radiation, and if it sees a lot of radiation over here, then that means there's nothing blocking it, right? There's absolutely no level in that vessel blocking that radiation. That's why it's seeing a lot of radiation. As I start to fill, I'm now blocking all of my radiation. So if I'm reading it over here, I'm not going to see much. So it kind of helped me when I was first learning to think of it that way. Just as my level goes up, counts go down. As level goes down, counts go up. So typically, and it all depends on the size of the source. I'm just going to throw some numbers out there. Let's say I have on an empty vessel, I'm getting ready to do a calibration. And I walk up my vessel and I do, I've reached process conditions. I've spoken to operations. They're getting ready to start up. Let's say before they started, I might have had 12,000 counts. This was completely empty, on atmosphere. I've started my detector up and I got 12,000 counts. Like, okay. Then they start they start pressurizing the vessel and getting everything in normal operating, getting ready to add product to it. Now I'm reading 10,000 counts. Well, that's normal, right? If you think about it, I've come under pressure and I'm starting to compress some of that vapor inside of it, so it's getting a little thicker in there, so it's blocking a little more radiation. So now I'm at 10,000 counts. At that point, I would go in and I would hook up to my detector and I would take a reading at that point. So that 10,000 points, I say take counts, and it's going to say 10,000. Then I'm going to tell it, what does that 10,000 equal? And I'll write inside my software, I'm going to say that equals 0% level. The detector's like, cool, I know where my 0 is. It's 10,000 counts. Then I start filling up my process. Well, actually, let me back up. I got two choices here. let's say I don't have the ability, to really feel it and watch it as it fills. Okay, that's out. It's just not going to work. I can get a good zero. I know my zero is good, but I can't do that. I look at the way my detector is installed. I look at the things going around me, and I know that if that vessel is completely full of process, I will most likely read zero, or I'm not going to have any radiation coming across that vessel. I can close my shutters on my source over here, and it's going to read a very low amount of radiation. It'll probably read somewhere around 100 counts, 150 counts. Another question. Told you I closed off all my radiation. I have no radiation. Why am I reading any counts? 100, 150. That doesn't make sense. I just turned everything off. It's because radiation's all around us. Okay, it's everywhere. We're around it all the time. If I ever walk up to a detector and I see that thing reading 0 counts and it's saying no radiation, in my mind, the first thing I'm going to is that thing's broken. It ain't working, because I will always have some sort of radiation. Radiation is present in everything. So we call it background radiation. So anyways, I close my sources. I take another reading, 150 counts or so. That's my 100%. It may not, at doing this, my stuff in between, my 0 and my 100, I don't know for sure if that's 100% accurate or not. But there is one thing I do know, is it's repeatable, because radiation does not lie. And as that vessel fills up, it's going to repeatedly do the exact same thing every time. So that 150 counts, it could be off a little bit, 5% or so in the middle somewhere. I could be off 5% or so in the center of my measurement. But for the most part, I am going to be pretty accurate. So a lot of times for 100%, we will do a closed shutter. I always prefer to fill my process up to that point. Okay, and the reason I do is because what if a little bit of radiation is coming through my process? But for the most part, that's if it's an option. On some of the processes out here, let's be realistic, you ask operations to fill it to 100%, and they look at you like you're crazy, because it's a dangerous process. They just can't go that high, so it's not an option. So you can close the shutters to 100% reading. All right, so we're going to talk about commissioning. So I was talking about Geiger counter a few times, and there's a picture of one. So that's actually my personal Geiger counter in the picture. This is a scintillator tube. Okay, the scintillator tube, I know you probably can't see me, my picture's small. That's the little brown tube at the end. Okay, that's what's reading. The scintillation technology is basically the same technology that's inside the detector itself. That's what it's reading. You also have a Geiger-Müller tube. Okay, this one is more sensitive than this one. Okay, you should be able to see me now. So this would be my Geiger-Müller tube. Okay, a little bit about this one. This is what I'll use for maybe just checking the radiation field around me, and I want to see that in milliriems per hour. So if I look at my Geiger counter here, I'll start at 0, goes 1, 2, 3, 4. This is my actual millirem field. Okay, over here, I'm gonna have my time scale, times 1, times 10, times 100. Yours will probably look a little different, but for the most part, it's gonna do the same thing. You guys, if you don't have it in the I&E department, if I'm watching I&E guys, you may not have one. I guarantee that your radiation safety officer in the plant does. Okay, so you do have one available to you. You just need to work out how to get it. Okay, so here's your scale. If I'm using this detector on mine, I'm reading these bottoms. Yours may not be like this. I'm reading, 0, 1, 2, 3. That's all the millirooms per hour. If I'm using this one, this is my scintillator. I'm going to read these top ones. It'll be a microrim, okay? So 1,000 millirem equals 1 rem of radiation, okay? 1,000 microrem equals 1 millirem of radiation. A lot of times, let's say I want to take a radiation reading on a vessel. I will take this. I actually have a long cord. You can see on mine. I have a long cord here. And I'll stand up top. My point wherever I can get my reading is actually towards the end. And I'll start off at 100%. I'll write on there where that is on my piece of paper. And I usually have little marks that I put on my cord to let me know how far I've moved it down. I'll move it down to that determined distance, let's say 6 inches or a foot. I'll take another reading. I'll write it on my piece of paper. I'll do that throughout my entire radiation span, or my entire measurement span. And I'll have that information. That way, later on, I need to figure out what's going on with this measurement. I've got a baseline. I know where I started on. I know where everything started at. And like I said, this will read in microrems. It's very sensitive. If I have a larger radiation field, sometimes I'll use this one. Usually for safety, I'll use this one. If I'm just walking around checking, I'll use my Geiger-Muller too. This will only read gamma rays. I guess I haven't really talked about gamma versus beta and alpha. Radiation, there's 3 main forms of radiation, right? You have gamma rays. That's what gave the Incredible Hulk all his power. Gamma rays will go through steel walls. It'll actually pass through stuff, right? It's very powerful. It'll penetrate. Beta can be stopped by, it'll be stopped by a very thin layer of plastic, okay? It'll be stopped by metal, any kind of metal. It won't pass through, but it's still radiation and emits radiation. So on this one, because it's got a metal housing around it, it'll only read gamma, which is what we're using in radiation gauging. That's what our detector itself has shielding around it that allows it to only read gamma rays. For safety, if I want to read beta, because beta can't penetrate metal, this one has a little thing on it that'll flip open. So I can see, okay, I got this much beta, I have this much radiation, and we'll close it, I have that much radiation, so I know that radiation I was seeing some beta radiation, right? Alpha is another form of radiation. Alpha, basically almost anything will shield alpha. Your skin will shield it. A thin piece of paper will shield it. The only way that you get alpha radiation into you is basically to ingest it. So if you touch something that radiation particles on it, by the way, your source holder, although it's emitting radiation, has no radiation particles on it. All that's inside of it, right? It's not going to radiate something to make it radioactive. But if you had, let's say that sort of capsule, never seen it happen, but if it did rupture, you'd actually touch the radiation particles itself, and then you would have to ingest that to get the alpha into you. Alpha is present in tobacco products. It's present basically all around us. It is all over the place. There is a lot of alpha. But anyways, that's a little bit about the measurement tools that we use. Let me go back to screen sharing. Okay. I should be back now. So I perform, like I said earlier, we just kind of talked about the radiation survey that I like to use. So I will go and I will do a radiation survey on the vessel. This should be done typically with an empty vessel. You want to do it with your sources open. I'll usually do them closed too. Why would I do it closed? If I don't expect to see any radiation, what's the point of doing that? Think about it for a second. I'm going to answer you. The reason I might want to do it closed is something else affecting my measurement. Do I have another vessel that's close by having an effect on my measurement? if I close the sources and I see it, then I know I'm getting that crosstalk. Is that a showstopper? Is that going to stop the job? Not necessarily. As long as your radiation fields can remain constant. So if this one over here, if it's coming from the source of itself, that radiation should always remain the same, even though I do have a little bit over there, unless I turn the sources off. Now, depending on how it's facing, if it's facing in a way and these vessels are really close and it's pointing directly at this side of my detector, and every time I change level in this one, this radiation field changes, then that could be a problem. But as long as that radiation field is constant, then I calibrate that into my calibration. Hopefully that makes sense, but that's something that you would just, as long as that radiation field that's hitting it doesn't change, and it is constant radiation field, then that just becomes part of your calibration. Your 100% number is a little bit higher, your 0% number is a little bit higher. So even with a closed shutter, you're just going to have a higher reading on your 100%. So it may not be a problem as long as it's not changing. Okay, I'm gonna start moving a little quicker here, so that way we have plenty of time for questions and answers. But so I record radiation levels typically at every foot, and then use those to compare to. We can use it to compare later on. So finding level during calibration. A lot of times, whenever we're calibrating, or what I'll do, the way I find level, I can use this handheld Geiger counter to actually find my level. So on this my diagram here, you can see my pointer. If I went and I taped, let's say every one of these hash marks were 10%, and I wanted to take a calibration point at 10%, I would take this to the vessel right next to my detector, right around my 10% point, and then I start filling it so that I'm at 10%. Whenever I suddenly I have a high radiation, let's say it's at 700 microrem, and then suddenly I see it drop to 20 microrem. I see this. I see it. That just tells me that, hey, my process fluid just filled up past that point. Operation stop. Filling. Let me take a calibration point here, and you can do that throughout the measurement. Let's say if you're not filling, what you can do is lower it. And you'll read, if you're up high, you'll read high radiation, you get to that point where the process is, suddenly you'll see your needle drop, you put a mark on the vessel to make sure it's not an obstruction in the vessel I'm seeing. Sometimes I ask our operations to move that level a little bit and make sure that point changes, and that'll tell me where my actual, that'll help me find level during calibration, or just as a extra verification if you just want to verify that your level's right. I talked about some of these a minute ago. So Geiger Mueller, this is an old technology. You used to see them all the time. They would use several of them together. They're not as sensitive as these scintillators. Scintillators could be much more sensitive. And just some of the gauges. So for the most part, we're starting to run out of time. So I'm at a good stopping point here. If we want to go into a question and answer, we can talk about different things, but that's a little bit about our radiation measurements. I covered things that I've covered is I've covered installation, covered the basic physics, and just a little bit of commissioning practices and things that we do whenever we're out there, things we look for, and some troubleshooting stuff.
We have one question from Roger.
Okay, Roger.
His question is it safe to assume the readings will be erroneous and inaccurate until you're up to process conditions? A lot of times the plant expresses concern when the levels are reading differently in a redundant application.
Yes. Yes. So we talked earlier about getting your, making sure you're at process conditions. And remember, everything affects your radiation, right? So the temperature of your vapor space is really what affects everything. So see my radiation field shifting. I've seen it shift 30, 40, 50%, even more than that as I'm coming up in level. It just depends. Let's say let's say my vessel's completely empty. I'll give you a couple scenarios. Let's say that we're in turnaround. Okay, we've had this detector on here for a while, and they have just come down, right? And they assumed everything was right. They've been trusting this gauge for years, and they trust it. Now they come down, and it stops coming down at 15%, and it doesn't get any lower than 15%. I'm like, well, heck, this thing's been inaccurate all along. It's 15% off. Not necessarily, okay? It was calibrated. Remember, it was calibrated to process conditions. So just because it's reading 15% and you went down, what could be happening right now? So let's think of different things that could be causing it to read 15, 30, or even 50 or 60%. If not as much radiation is coming across the vessel as normal, then I'm going to read a higher level, correct? So one scenario is, let's say I have an agitator blade in there, and now as I've come down, my agitator blade has stopped, and now it's blocking some of the radiation. Okay, that's going to make it read inaccurately. That might make it read 30% or whatever it may read. Let's say that I had Doutherm that was very hot inside of the outside of the as a shield around using as a cooling element or whatever they're using it for. Well, it's going to have a lower density at warm temperatures and a higher density at warmer density. Sorry, density is going to be higher whenever it's warmer. It's going to be lower density when it's colder. So that means radiation isn't passing across. It's going to be blocking more radiation when it's cold. So there's a lot of different things to take into account for that.
Several more questions.
Okay.
As well.
All right, let's go on to the next one.
Okay, great. Let's see. Cody's asking, is it easier to calibrate points by using Packware software or a handheld communicator? And how many points is necessary to have?
All right, Cody. So you're saying Packware, so I assume you're talking about a Vega gauge. The question was, is it easier to use a handheld or use a software? Really, I usually recommend using the software, just because you can see a little bit more. You have a little bit more that you can see on there. And honestly, I don't usually trust the handheld so much with the different versions of handhelds, heart communicators. I would prefer you to either use the display alone on the newer style Vegas, or use the Packware software. Obviously, the easiest way to do it is going to be use the software because it shows you all the information at one time, and it's much easier to see. So yeah, that would be. I'd recommend going ahead and downloading it. It's actually available on their website, and there's no cost to it. So.
Roger asks, can you briefly give us an overview of building a level curve for calibration purposes?
Yes. So to give you an example of building a curve, so if I was going to start off, and let's say we're going to start off at, we're going to do 4 points on this one, okay? So basically on this particular application, I need to know about where it is at 50. We'll say they run at 35% most of the time, and I just want to get enough points in there to make sure that I'm accurate between these points. 4 points is typically plenty to get in most calibrations. So I would get up the process conditions. Let's say we started with a vessel completely empty. I get up the process conditions. At that point, I'm going to take my 0. The next thing I'm going to do, and that's going to be in counts, next thing I'm going to do is I'm going to mark out my vessel span. I'm going to know where physically on the vessel my 25% is. I'm going to actually take this Geiger counter to that vessel right there. So raise and level. When I see it hit that 25% part, I'm going to say that's where my level is. I'm going to put that count point in there. I'll do that at 50. I'm going to do that at 75. At 100, I can either, if they're willing to take it all the way to 100, I'll take 100. If they're not willing, I'll do a close shutter at that point. And that would give me a good curve of a 4-point calibration.
Perfect. Mark is asking, CS-137 primarily decays by beta emission. Is it the beta emission that we're measuring, or are we measuring beta and gamma emission?
We're measuring gamma only. Okay, so you're right. It is going to decay at beta, but we don't really care about that, our main decay point, because that detector is shielded in a way, and that beta will never make it across that vessel. It'll never penetrate the detector itself. So we've basically canceled out all of the beta. We've canceled out the beta decay and all of it. The only thing we're measuring is gamma. So that's all we care about.
Hector is asking, can the level detectors be calibrated by opening and closing shutters when the vessel is empty?
It can. So this is a good question. We're asking, can we calibrate with an open and closed shutter? My answer is going to be, if I am looking for repeatability, okay, and I want it to be repeatable, I'm not necessarily concerned with it being 100%. When it says 50%, do I need it to be exactly 50%? Not 49%, not 51, I need it to be 50. If I need to be that accurate, then I need to take a calibration point at that spot. But if I just need to know about where it's at, whenever my gauge is reading 50, if it's okay if I'm reading, if my real level is 48 or my real level is a little bit higher or lower, it's going to give me completely repeatable with a 2-point calibration. Completely. It'll be repeatable. It'll read the same every time. So it really depends on the accuracy that you need, and on which of those that you choose, and a little bit on the installation itself. You know, let's say I'm comparing this. Redundant measurements came up a second ago, having a radar gauge connected to it, reading with it, or any other kind of measurement, maybe a DP. If I'm doing that, operations are going to want those two numbers to match. So I may want to do multiple points at that point to make sure that they always match. Might want to take a multiple point calibration. Or if it's non-linear, let's say I'm measuring into a cone, my measurement's not going to be linear. At that point, I need to take multiple points. But if it's a linear measurement and everything is straight up and down, 0 and 100 is typically just fine as long as repeatability is okay.
Thanks for all the questions, guys. This is great. Walter is asking, what will be the lowest level of radiation a detector would see when empty and still be a usable system?
The lowest level that it can see when empty. So you're saying at the 0%. So that's there's really not a straight answer for that. I preferably, okay, the more radiation I see, the better. So I like to see 1,000, 1,500. I like to see good numbers. I have made measurements as low as 200 or 300. Well, maybe not that low, maybe about 600 counts, 500 counts, 400 counts. I have seen them make measurements and be reliable at those points. If I am making measurements and those are the counts I get across, typically me being in the field, what I will do if I see counts coming back that low, I'm going to go back to the math. I'm going to go back and make sure that it was designed at a point that I expected it to see it that low, and make sure that we're not missing something. So I don't know if that directly answered your question or not, but it can read pretty low, but it's going to affect your resolution when you start getting low. There are times when we know we're going to have low count readings and we don't have a lot of resolution, and it's just it's a design decision.
Okay. And Roger is asking, what are some of the most common issues and solutions on nuclear level applications?
Common problems?
Most common issues and solutions.
Okay.
So problems and
so different kinds of problems. So typically, as time goes on, probably one of the most common thing that's going to happen is you're going to go a little bit inaccurate due to buildup in the vessel. Okay, so if you don't put a nuclear gauge on something that's an easy process to measure typically. It's usually on something that's hard to measure. That's why we chose nuclear as a technology. So there's going with that. There's a lot of times there's going to be you might have buildup. a solution to buildup would be what we call standardization. So standardization is a type of calibration that does not, you're not doing a full calibration. What you're doing is you're saying, okay, this thing is rating 50%, but my real level is 60%. Okay. My curve, I performed a curve earlier. So when I first installed this, my curve was accurate. That curve is never going to change. So I don't need to build a new linearization curve. All I need to do is shift that curve. So I can do a standardization, and that shifts my entire curve to make up for that difference. Same is true if I have maybe my vapor space changed, and now I'm running a less dense vapor space than I used to, or more dense vapor space than I used to. Then you would use that standardization. On some gauges, they call it real value correction. Just about every gauge is, regardless of the manufacturer, is going to have some sort of name for it, but it's a single point calibration. That would probably be one of the most common inaccuracies. Another one would be maybe not an inaccuracy for the gauge itself, but people don't believe it's right, and that's just going to be troubleshooting through the process of figuring out why those differences are different. Sometimes it is built up, sometimes it's a lot of times it's something else. You know, what they're looking at is inaccurate, and with the gauge itself is actually reading what it's supposed to. So.
Anything else on that one? Good.
No,
okay.
Unless he has more.
Okay. Cody is asking, do Vega nuclear detectors work like a Vega radar when calibrating the false signal suppression?
No. Okay, so they're completely different technologies. The similarity on those is going to be between. So the question was, in case you didn't hear Emily, is calibration on a Vega nuclear gauge going to be the same as a Vega radar gauge, or is the echo curve going to look the same? It's not. False signal suppression, none of that is there. The software itself will look the same, and they built the software in a way to where if you understood radar and you understood how to navigate the radar software, you'll probably be able to figure out the nuclear software as well. They've made it very intuitive, and you're basically just going to be building a linearization curve in the software.
Okay. And Roger asks, if we are having an issue with a nuclear application, can you give us a good contact for having someone come out to assist us?
Sure, we'd love to do that. So Sarah Jerome is our service coordinator. Okay, Sarah is she dispatches all of our service guys. Me myself, you can. One thing about us is, guys, we are willing to answer your phone 24 hours a day. So if you have questions, you're stuck. Cody, I heard you say earlier that you're fixing to do a calibration. You can call us. You can get a hold of us through Emily. Get a hold of us through Sarah. You can on the website. I will give you my phone, my personal cell phone number right now to everybody listening. I'm gonna give you a second to get a pen ready. My number is 713-299-0724. My name's Joey Blair, and I primarily work in the unit. I may or may not be the one to come out and help you, but I'm more than glad to talk to you. Like I said, the main contact, if you need to actually schedule service and you want somebody to come out and do commissioning, it's not just a quick question, then I would take that through Sarah herself, because I wouldn't do any of the scheduling. I'll be more glad to talk to you. My email address is Joey Blair, Joey Blair at techstar.com, TECHSTAR. Like I said, more than willing to answer questions, or maybe to let Sarah know that you're interested in scheduling, but all of our scheduling will be through Sarah.
Perfect. And one last question from Roger. Are the electronics susceptible to heat issues, and what are the best resolutions you have for this, if so?
Great questions, Roger. So yes, they do have a limit on the electronics. Heat can be a factor on a nuclear measurement. So 60 degrees C is the maximum temperature you want to see on a set of electronics. But even, and a lot of people don't realize this, what's even more sensitive to that than the electronics is your fiber bundle itself. Okay, your fiber bundle stops at about 50 degrees C is where the fiber bundle could over time start getting so damage, which where it means that's just not getting as much radiation can travel through those fiber optics inside the bundle. Resolutions is just about every manufacturer has some sort of, they can do different kinds of shieldings. They can do water cooling, and they have ways to do different kinds of air cooling to mitigate the heat.
Perfect. Thank you. Alrighty, it looks like that's the end of our questions. Joey, thank you so much for spending the time with us today. Before we wrap up, Roger does have some remarks that he'd like to make. So Roger, we'll go ahead and give you the floor.
All right. Well, first of all, I want to thank Techstar for putting this on for us and working with us to get it done. Second of all, I'd like to thank everybody for attending, taking the time out of your day to join the session. For those of you that requested PDUs or personal development hour certificate, Mr. Shane Gonzalez will be emailing them to you shortly after this, so be looking for those. That's really about it. I look forward to working with Techstar and putting on some more great training for everybody that's looking for it.
Perfect. Thanks so much. We appreciate the opportunity to present today. And everyone enjoy the rest of your day, and we'll be talking to you soon, hopefully.
And if you want to come see the training unit, just holler at us. We'd love for you to come check it out.